Now that we've figured out how to find the best model for any given data set, there are a few things need to watch out for. And there are going to be three of them: influential points, extrapolation, and causation. We'll start with influential points. This is an example using Gesell scores, right, which is a standardized test to score or measure intelligence correlated against the age of the first word. So here we have, how old a child was when they first said their first word. And then later on, I forget, it's maybe 10, 12 years old, all right, they might take the Gesell score or the Gesell test, right, and here's the two variables plotted against each other. And what we can do is look for any unusual points to investigate. Influential points are really the two-variable version of outliers. So we can look at this data and we can say, well, those 2 points seem kind of extreme. This one's sort of extreme on the x. This one is sort of extreme on the y. All right, now, for one variable, we had a formula to determine outliers. Not so much for two variable. It's more of a judgment. We just have to say, oh, that's kind of, out there. This is sort of extreme. Let's see. We have to investigate. Now, this turns out to be child 18 and 19, which in the data list are those two. What we want to do is perform a linear regression using all of the data. Then what we want to do is remove each point of investigation one at a time and then recalculate the linear regression. So what we'll do is we'll take out child 18, recalculate the linear regression, and that would look something like this. And you definitely want to plot it, the linear regressions. Then what we can do is we're going to put child 18 back in and then take out child 19, recalculate the regression, and then it looks something like this. And what we want to do is determine what difference removing that child made. And if it made a big difference, we can label that child, or that point, as an influential point. It has a lot of influence on the regression. So already we might suspect that child 18, which is the green, seemed to have more of an influence. But what we can do is calculate the difference. And what we're going to be focusing on are the slopes of the lines. So if we calculate the percent change between the slope, here we have our 0.997 when we remove, right, so here's our 0.997. 1.127 is when all the data is included. So this is the difference as a percentage, right, and so it changed by 31%. Where when we remove child 19, it only changed, the slope only changed by 6%. Positive or negative just means, positive change, negative change. That doesn't make too much difference. 6% isn't that much, but, this is almost a third, right? That's actually pretty huge. So we could probably pretty clearly say child 18 is an influential point in this data set, or child 19 really isn't. Now, once we've determined that, then we have sort of a discussion. And we have to decide whether to keep or discard, providing proper reasoning. So one way of looking at this is we could actually see what influence this has not only on the slope of the regression line, but on correlation and determination. If we look at our correlation coefficient, we go from 0.64, negative 0.64, down to very weak, 0.33. Ooh, that's pretty weak. And then if we look at how well the model fits using our coefficient of determination, we go from weak to almost non-existent. So this one child, child 18, is having a really huge impact, right, on this model. And really, if we're going to use this model to predict, how good of a prediction is it for most of the kids? Really not so good. I mean, if we take out that child 18, our predictive power is very low. where if we keep it in there, it makes it seem like it's higher than it really probably should be. I think there's probably a good argument for removing child 18 because it's just not going to produce a model that is a good model for most of the kids. That's influential points. Now our next issue is extrapolation. Now we're going to use mouse population as our example, and maybe we're looking at a big field somewhere and somehow we're getting estimates of the mouse population over time, months, almost 3-year time period. And we can graph it and it'll look something like this. And we might be given a question where we try to predict the mouse population using a linear model, right, after 75 months. So we don't have to pick the best model, right? We're told to use a linear model. So easy enough, right? We do our linear regression. When x is equal to 75 months, we plug it in, and we get our prediction of over 1,000 mice. Let's graph it. All right, what we're going to need to do is change the scale so that we can fit this point in. And there it is. You can see it's really far out, right? That's what extrapolation means. We have sort of a zone around our data. Extrapolating means going beyond your data, and this is actually quite a big difference beyond the data, although it's still on the prediction line. It's just really far away. So what we can say is confidence in this prediction is very low because there's a significant chance that the behavior of the population will change before 75 months has passed. Right? There's excessive extrapolation. And what do I mean by changing behavior? Well, what happens if this is a classic predator-prey kind of behavior and it's actually going to do something like this? Right? After, just a short time, it's really not going to be very linear at all. Right? There's also the possibility that maybe it's more of a logistic, right? And it just kind of plateaus out. In either respect, because you've gone so far from your data, you simply don't know whether the behavior is going to be the same or is it going to really change like I've shown here. Our third issue is correlation versus causation. And the example we're going to use is something I saw on the internet, so it must be true. A study is conducted and has found that there is a strong positive and linear correlation between the per capita chocolate consumption annually and the number of Nobel Prizes awarded in that nation. Turns out we have a nice correlation coefficient of 0.79. So here's a question. Leaders in a particular nation want to see an increase in the number of Nobel Prizes awarded to their nation. They hear about the above study and pass a law requiring every citizen to increase their chocolate consumption. Is it reasonable to expect their plan to work? Please explain. Well, the answer to that, of course, is no, absolutely not. It seems very implausible that chocolate consumption could actually cause an increase in Nobel Prizes. Just because two variables correlate does not mean that one causes the other. Correlation is not causation. It seems much more plausible that a third variable, lurking or confounding, is in play. A possibility would be that median income within the nation is that third variable. If the average income is high, there is more disposable income for both chocolate and funding advanced research. If the average income is low, then there's little disposable income for either. So correlation is not causation. That's a big problem sometimes when it seems like it should cause, and maybe it does, but just because two variables correlate actually tells you nothing necessarily about causation.